Okay, so my lab is called the Collaborative AI in Robotics Lab. The idea is to try and find ways to support multi-agent collaboration for AI agents and for robotic agents as well, in a special case. So in the lab, we have different types of work. One thread of work thinks about considers collaboration in multi-agent AI domains, and specifically we work a lot with multi-agent reinforcement learning settings. Itai here is a student with my group working, for example, on trying to think how multi-agent reinforcement learning can be used to optimize energy systems and the electrical network using reinforcement learning agents. That's one thread of work, and the other thread of work has to do with our robots. This is seen from our lab where we have manipulators and we have mobile agents. And the idea is the same. We want to find frameworks and settings by which these agents can collaborate, can understand how to optimize their behavior while considering the other agents in the environment. And the thing that leads these two threads of research is the fact that I'm really interested in understanding how these high-level concepts, these abstract models that we come from with the set of tools that we have from multi-agent planning and multi-agent reinforcement learning, how they translate to the real world. So in the electrical system, for example, we have to consider the constraints that are involved with optimizing electricity that runs through the transmission lines and losses that are endured by the fact that we have to charge and discharge our batteries, etc. And for robotic agents, it's the same. We have to come up, we have to consider the fact that blocks world, picking up a block and placing it on another block is a very hard task. It's not something that we can just consider and wave our hands and say that's going to work. We actually have to figure out how to model that and integrate these high-level tools into the planning process and combine the execution, and things become very complicated. So the kind of thing that we do in the lab, and I'll dive into one of the projects in a minute, is this interplay between the theory, the symbolic AI methods, and of course we do a lot of statistical learning as well, but we always consider tests where that's not enough. So we have our symbolic search method and reinforcement training methods, but we consider how they actually apply to applications that we care about. And as I said, currently, I'm most passionate about the energy systems and robotic agents. And this interplay really is fascinating because it allows us to understand how to enrich our models, and then how to use them to solve the problems that are too complex to solve using just simple control commands, or even learning is not sufficient. This is a crowd where this slide is redundant, but I just want to say that it's here because we all care. I mean, we all care about or work, I guess, because we're here. We all work with agents, which means that what we want to come up with is a policy that tells our agents what is the best thing to do, what are the good actions to perform based on an interaction with the environment. And the algorithms that we come up with have to be relevant to the specific setting that we care about, but they are general. So the product that we want to come up with is a general enough algorithm that we can use for the different settings that are involved. And this for a single agent is already very complex, and things become even more complex when we have other agents in the environment. And I know for many of us, multi-agent AI, multi-agent reinforcement learning means different things. I tend to focus on the non-adversarial settings where we have conflicting rewards. We have each agent has some reward or optimization criteria, but there is either an incentive to collaborate or at least an incentive not to interfere with each other. which is already very rich and it gives us a lot of problems to work on. And one of the things that I, when I started my lab, I kind of thought, well, what is it that I want to accomplish? So one of the things that I wanted to accomplish, at least for the robotics agents that we have, is equipping agents with the ability to be helpful to each other. So I envision a framework where robotic agents would be able to kind of understand how they can assist each other, how to request assistance, and how to interact. And I want them to do that autonomously. And this is a long-term plan, and it's work in progress, and it's going to take a lot of time to work on. But the idea is that I have to start somewhere. So first of all, what are the kinds of settings that we care about? For the robotic agents, we are always interested in complex tasks. So tasks that have some horizon. So it's not just about picking up an object. It's about doing some complex manipulation tasks in the environment. It's usually a dynamic and stochastic environment. Sometimes I have the model of the stochasticity, sometimes I don't. And I'm very interested in settings where we have multiple agents with different capabilities. So this wouldn't be a swarm, if you guys are familiar with the term, wouldn't comply with the requirements to the kinds of settings that we would want to work on. There is some a high level and complex reasoning that has to happen in the kinds of settings that we are interested in. So the first step, right, this is the long term. This is going to take time. We're going to market, we're going to trade, then we're going to interact. But for now, the first step is just understanding value. So, where does value come from? Reward functions that we're used to working with, where do they come from? This is something that I remember as a student, as a PhD student, and as a postdoc, right? We are used to receiving an MDP or a POMDP, and then there's this reward function that we take as inputs. I'm not even talking about the transition function, right? That's also something that we can discuss greatly, but where does this reward function come from? And I was starting to think, what would be a way for me to actually, instead of just saying 1 or 3, I wanted these functions to have some meaning and understand where they come from when I try to apply them to robotic settings. So the first test that we started working on, and this is a long-term venture, is talking about something that we call value of assistance, which should sound familiar to you, which I know what is the term I'm referring to, which we all know in this context. Value of information, right? So an adaptation of value of information to robotic settings. And I'll have a slide where, I know people here have done some work in this, and I'll show how that relates to that. So I'm going to show you some examples of value of assistance in robotic settings, how we formulated this in a very general way, so people can use it off the shelf, just even if they just want to use our formulation. I'll show you 2 instantiations, 2 settings, and the next steps. And I'll start with an example, just to make sure that we see that AI and our tools and the bag of tools that we come from are very relevant to robotics research. So I know you are probably haven't started. Who does robotics here? Like, who has dealt with robots? I know, like, who has, okay. So try not to participate. We have these 2 navigating agents, and they are tasked with the need to follow a trajectory, a path of waypoints. Each has its own waypoint, and they are operating in a mapped environment with an obstacle. And I have the ability to intervene by providing localization information. So what we see here is how uncertainty increases over time. This is something very common in navigation settings, where robots, as they move in the environment, they gain uncertainty, inherent uncertainty, that they are the environment. And the question that I'm asking you, now I have an ability to provide localization information. So I can tell one of the agents exactly where it is. Which agent should I assist? Agent 1 or agent 2?
1.
1, why?
Because the obstacle is closer.
So 1, because the obstacle is closer and there is greater risk of collision, right? Because there is uncertainty, there is, yeah?
We care about not the risk of collision, but the difference provided by the localization. I'm not 100% sure exactly what the diagram represents.
So there is a trajectory that they need to follow.
So when you have the white star, that's when they would get information.
Yeah, so step number 3.
That would reset the size of the uncertainty circle.
Yes.
So then it's unclear to me, but it may be that you should have a case where getting that information helps, but doesn't give it enough information to actually know whether.
So the agent is gain enough uncertainty going along, so it wouldn't really make a difference by the time it takes to get to the goal.
Value of information is always about the decision and the choices available.
Yeah.
And if the choices available are to move forward or not, adding information when it doesn't change the decision has no value.
Oh, it can change the decision because it has to navigate between the
Right, if it doesn't change, I'm saying, so the question is, does it change the decision? And the question is, do I move forward to the next,
Yeah.
to the next block? I'm not.
Okay, so let's assume the robot is going to move to the next block, but it can, based on its information, it can decide how to move between waypoints. So one answer that we already got is that this agent would need assistance, is higher need of or assistance because of its risk of collision. Another answer for somebody in robotics, that's actually the answer I get first. If I give this talk in AROS, this was the first thing I got, was the fact that actually this agent is the lesser need of assistance because it has a landmark here it can use for localization. So the answer is that it really depends on the capabilities, whether I'm going to assume that the agent is going to use that information or not, and on my ability to assist, right? So that's kind of the point that we're trying to make here. A second example, which we won't have time to dive in, I see my time is going to run out shortly, is something that we're working on right now. We call it value of assistance for grasping. Also, this is a collaborative grasping setting where we have one agent that had to pick up an object, and this object has a known form, but there is and the initial location is known, but the agent, which we call the actor, picked up the object and then dropped it. So now, instead of knowing the location, we have some belief, distribution over the possible locations. And the question that we ask is, we have another agent in the environment equipped with a sensor. What would be the best configuration, so the best position of the sensor that would give the highest value information for the grasping task? So here, for the initial step is quite simple. It's we have an actor, he picked up the object was dropped, and we only ask the question of what is a single observation that would be most helpful before a grasp is attempted again. And future extensions, of course, involve a more elaborate interaction. But the point is that we have this recipe for formulating this value of assistance setting that depends on the effect an assistive action is expected to have, the estimated policy of the actor based on the information, and the expected effect that this will have on the state of the environment. And as I said, this is not, from the perspective of AI, this is not a new concept on its own, right? Value of information, value of helpfulness, and value of communication developed by Reut. and others, but I know who's is here. I'm sure there are other people to give credit to. And the specific novelty that we want to offer here is its instantiation to the robotic agents, to their knowledge representation, to the way they make decisions, and to the specific assistive actions that can be offered. Okay, so this slide is actually meant to just make sure that we understand that even though it's a robotic setting that I'm currently interested in, the formulation is very general. We have two beliefs because we have an actor and we have a helper, and the helper needs to take its belief into account when assisting, but it has to make sure to take into account the way the actor is going to respond, how the belief is going to be affected. A lot of discussions that I'm planning to have with Mishai on this. And then what we are going to examine is the difference between the expected utility with assistance and expected utility without assistance, again, instantiated into the specific reasoning process of the robotic agents. And this is just a formulation that is a bit simpler because when we give information, we don't change the state of the environment. And this idea has so far led to two threads of work. One of them is for the navigating agents that I've showed you, taking into account the fact how they reason about their position in the world, here using the Gaussian process and the accumulated past cost. I had a lot of integrals in my work recently. So this is the biggest transition. Like this paper, if you look at it, it has a formula with 5 integrals. I took a deep breath. Muhammad was a leading student in this work. Oh, sorry, Adi was a leading student in this work. And they came to me with this formulation. I was like, wait, what about sigma? Is that not sufficient? You know, we had to switch to a continuous state, so a lot of integrals, but we managed. We went through it. So this was an IROS 2023 publication where we actually showed that our ability to estimate value of assistance was highly correlated with the actual assistance. And I have a video, but maybe we don't have time for the video. It just shows you that it's actually something that we run. How much time do I have? I'm sorry, because of the interruption. Okay, so I won't show you the video. And then we have the same kind of setting for the grasping. A lot of Asian filters, a lot of stuff going on here with the need to account for what's going to be the predicted observation. Lots of fun. I'm very happy to talk more about the details if you're interested. This is still work in progress. But this is what it translates into. We take a set of objects that we know the initial location of, and we try to predict based on an observation estimation, right? When we have a quantity, we try to kind of predict what is going to be the observation. So we actually have an observation function here. We need to predict what is going to be the effect of observing an object. And then we have to come up with an automated way of understanding what is the informative value of an observation. So these all look very, very similar and are very confusing to our decision-making process. And this is something that we need to take into account when choosing a configuration from which to collect an observation. So it's, if you just look at, standard methodologies from computer vision that just look at, for example, the different intersection of unions, so like what is the overlap, that's not going to give us enough information. We have to come up with new methodologies that actually extract the value of information with regards to the specific task of grasp, which is where it becomes from, which is how we move from value of information to value of assistance. It's a task-oriented sensor collection or observation collection process. So it's a lot of, it's fun and a lot of things that have been done, but still a lot of work to do. So far, we had a set of possible, this is the only thing I managed to keep discrete. so far is the set of possible assistive actions. Of course, my students complain that the world is continuous and it's not a set. It's an infinite set, so we have to work on that. We so far had a one-time intervention, so what is going to be the value of one intervention? We need to come up with an idea of how to account for long-term interactions. We have a two-agent setting so far, but only one objective. So it's not really a multi-agent setting, it's a multi-agent setting in the sense that each agent has its own capabilities, but we haven't considered that the helper might have its own objective, so that's one of the next steps. Yuval is working on that. We really want to come up and go back to the safe zone of actually coming up with some formal guarantees. So far, our work has been empirical, but we want to be able to say, okay, this is an observation that is guaranteed, or this is a predicted observation, this is a sensor configuration that is predicted to achieve at least some guarantee and some bound. So this is what we've been up to, and I'm done.